We walk on it, build on it, and pretty much trust it completely. But the ground beneath our feet is actually speaking a kind of hidden language. And understanding that language, well, it's pretty much the only thing that stops our world from sinking. Today, we're going to decode the surprising science of soil. We trust the ground to be, well, solid. But every now and then, right, you see it. A building cracks, a road buckles, a whole slope just gives way. So why does something that seems so firm and reliable suddenly fail? The answer is a hidden conversation happening right under our feet. So, this whole mystery starts to unravel when we stop thinking of it as just dirt and start seeing it as a complex engineering material. See, soil has properties, it has behaviors, and yeah, it has breaking points, just like steel or concrete. We just have to learn how to read its signals. So, what's the key to this mystery? It's not about how hard the ground is, it's actually about how it reacts to one simple, incredibly powerful ingredient: water. The amount of water in a soil can totally change its personality, taking it from a stable foundation to a dangerous fluid. Okay, so depending on its water content, a fine-grained soil can exist in one of four different states. It's kind of like water itself, you know? It can be ice, liquid, or steam. For soil, the changes are just as dramatic and way more important for anything we want to build. Let's start with bone dry. In its solid state, soil is brittle. Sure, it's got strength, but if you try to work with it, it just crumbles and cracks. There's zero flexibility. All right, now let's add just a little bit of water. We're now in the semi-solid state. The soil particles start to cling together, but it's still way more solid than it is pliable. If you try to mold it, it's probably going to break apart. And this brings us to the really crucial state, plastic. With just the right amount of water, the soil becomes moldable. You can roll it, you can press it, you can reshape it without it cracking. It acts just like perfect modeling clay. And this property, plasticity, is the key to everything. But if you add too much water, you cross one final line. The soil enters the liquid state. It loses its shape completely, it can't support any weight, and it starts to flow like a thick soup. This is where foundations fail and mudslides begin. Now, for an engineer, saying a little water or too much water just isn't going to cut it. They need precision. And that's where the work of a Swedish scientist named A.M. Atterberg comes in. Way back in 1911, he developed this simple, absolutely brilliant system to measure the exact moisture content where these changes happen. The first tipping point is what we call the plastic limit. It is the exact moisture percentage where the soil stops being crumbly and actually becomes moldable. Think of it as the doorway into that useful plastic state. The second tipping point, and this one is often the most critical, is the liquid limit. This is the exact moisture percentage where the soil loses all its plasticity and starts to act like a liquid. It's the point of no return for holding a shape. But here's the really brilliant part. The magic isn't just in these two limits by themselves, but in the distance between them. That range of moisture where the soil stays plastic gives us a single powerful number. It's like a unique ID that tells us almost everything we need to know. And the process to find this ID number is surprisingly simple. In the lab, geotechnical engineers first figure out the liquid limit. Then they find the plastic limit. The last step is just simple subtraction. Liquid limit minus plastic limit. And that difference? That's the plasticity index, or PI. This single number tells you exactly how sensitive a soil is to water. So a low PI means the soil has a really narrow window where it's plastic. It goes from semi-solid to liquid really fast. A high PI means it stays in that workable, clay-like state across a much wider range of moisture. Let's look at a real-world example from Braja Das's foundational engineering text. For a sample called Soil A, the liquid limit was 30%. That means it turns to liquid when 30% of its weight is water. Its plastic limit was 22%, so you subtract them and you get a plasticity index of 8%. Now, for an engineer, that 8 isn't just a number, it's a clear signal. It tells them this is probably a silty soil, one that's not going to cause too many problems. So the crucial point here is that this isn't just some academic exercise. The plasticity index is one of the most fundamental tools engineers use to design safe and stable structures. We're talking everything from skyscrapers to highways to dams. This table shows you exactly how they read that number. A low PI, under 10, like our 8% example, means you've got a silty, less problematic soil. It has a low potential to shrink or swell. But as that PI starts to climb above 20, oh boy, now you're dealing with a highly plastic clay. That kind of soil acts like a sponge. It swells up like crazy when it's wet and then cracks when it's dry. A total nightmare for any foundation you try to build on it. In fact, the PI is so essential that it's a cornerstone of the Unified Soil Classification System, which is basically the universal language engineers use to identify soils. It lets them predict behavior, calculate risks, and design foundations that can actually handle the forces at play in the ground. When you kind of zoom out, you realize just how profound this simple concept is. Atterberg's limits and the plasticity index, they aren't just numbers in a textbook. They are the invisible foundation holding up our entire built world. So much of the safety and stability that we just take for granted, the roads we drive on, the bridges we cross, the buildings we live in, all of it rests on decades of engineering knowledge about this one fundamental interaction, the simple yet powerful way that dirt plays with water. It really makes you wonder, doesn't it? The ground beneath your feet is no longer just solid ground. It's a dynamic system, speaking a language of plasticity, limits, and water. What other invisible forces are out there, shaping the world around you, just waiting to be understood?